Designing a GPU accelerator integrated circuit (IC) requires balancing throughput, memory bandwidth, power efficiency, and silicon area to map parallel workloads efficiently. The modern architectural process involves optimizing specific hardware primitives, such as vector units, memory hierarchies, and interconnect fabrics, to prevent performance bottlenecks. 1. Compute and Parallelism Strategy. SIMD execution. Maximize throughput by deploying fine-grained, thread-level parallelism. Use hierarchical thread mapping, e.g., warps wavefronts, to hide memory latencies through fast context switching. Domain-specific hardware units. Integrate specialized processing blocks like tensor cores for matrix math and low-precision floating-point arithmetic, e.g., FP8, FP4. Sparsity support. Design logic that prunes zero-valued parameters and bypasses their computations, significantly boosting operations per second and reducing power consumption. 2. Memory hierarchy and data flow. Compute to cache ratio. Tailor cache sizes to expected workloads. For example, data center GPUs require large shared L2 caches, while edge devices demand tightly coupled software-managed memories (SRAM) to maintain power efficiency. High bandwidth memory (HBM) utilize 2.5D, 3D die stacking to provide high bandwidth off-chip communication and prevent memory starvation. Data reuse dataflow. Implement architectural dataflows, e.g., row stationary or systolic arrays, to maximize local data reuse, minimizing trips to the global memory, which is the primary driver of dynamic power dissipation. 3. Interconnects and scalability. On-chip networks (NOC) implement highly provisioned mesh or torus NOCs to facilitate low latency, single-cycle data delivery between processing elements (PEs) and cache banks. Off-chip interconnects die-to-die and multi-node incorporate high-speed, cache-coherent interconnects, e.g., NVLink or packet-switched routing to scale workloads across multiple GPUs while mitigating communication overhead. 4. Power and thermal management. Clock and power gating. Design the IC to dynamically power down unused hardware blocks, such as specific SIMD lanes or tensor pipelines, when executing scalar code or handling sparsity. Dynamic voltage and frequency scaling (DVFS) establish thermal zones and power capping logic to maintain sustainable peak operations, as thermal dissipation has become the primary limit to scaling. Packaging alternatives. Evaluate chiplet-based architectures to decouple compute logic from control logic, which yields higher yield rates and better thermal management than monolithic dies. 5. Architectural trade-offs. Area versus flexibility. Balance the trade-off between flexible, programmable compute units and fixed-function ASICs. While ASICs offer superior peak efficiency, they are vulnerable to rapid algorithm obsolescence. Precision handling. Include flexible hardware that can dynamically adapt data precision depending on algorithmic needs to optimize execution speed versus accuracy.